Welcome to NPTEL course on fractals and multifractals. In the last lectures, we have defined Hutchinson-Bansley mapping, and we obtained that Hutchinson-Bansley mapping is a contraction on H of x, the hyperspace of x. Now, let us prove it has a fixed point, and thereby we will prove what is an or will define what is an deterministic fractals. So, these lectures will give the definition of deterministic fractals and their example, some of the example of deterministic fractals. Okay. In the last lectures, we have defined the Hutchinson mapping on H of x. I just recall it. Here H of x is a hyperspace of H, where x is a complete metric space, F is a mapping from H of x to H of x defined by taking the union of F k's, where each F k is a contraction on the complete metric space x. Now, let x comma d be a complete metric space and H of x comma H d be a associated Hausdorff metric space. That means, this is the collection of all non-empty compact sets of x, and the Hausdorff distance is induced from the metric D. If the self mapping F defined in the previous slide is defined by the iterated function system, because the F is defined the union of all the contraction mappings. So, x together with the finite set of contraction mapping, we can call it the iterated function system. Then the mapping F has a unique fixed point A star in H of x. That is, there exists a unique non-empty compact subset in H of x such that F satisfying the self referential equation. That means, A star equal to F of A star. That means, this Hutchinson map is defined as union of F k's. So, this A star can be written as union of F k of A stars, k equal to some 1 to n numbers n. Moreover, for any b belongs to H of x, limit p tends to infinity, F p composition of F of b equal to A star. That means, if you are taking any random set in H of x, then what is F composition b? The F composition p is an F composition 2 means it is F of b. Find the image of b under F and again find the image of F of b under the mapping F. In general, F n of b stands for F of n times F of b. We need to close it. This composition, where that means the nth composition of b. If this n tends to infinity, here it is the p tends to infinity, this sequence converges to the fixed point A star. Now, one can observe that we are taking the finite union of contraction mapping, and we need to prove that F is a contraction on H of x, then we can establish that F has a fixed point in H of x and the fixed point is this one we can prove. But for this one we already proved the enough results. So, let us start with the summarize the result. So, since given x is a complete metric space, therefore, the hyperspace of x and Hausdorff distance of all non-empty compact sets of X is also a complete metric space. If X comma D is complete, then H of X comma H D is also a complete. So, here each mapping F k is a contraction, that is there exists a constant in between 0 and 1 such that the distance between f k of x and f k of y less than or equal to this one. That means each mapping is a contraction with contraction ratio C k, each is less than 1. We can take maximum among all the C k and we can call it as C. Now, as per the definition of H B mapping, f is a function from H of x and we need to take the union of f 1 of a. But we already arrived this result, the f is a contraction if f 1, f 2, f n is a contraction, then their union also contraction, which we proved. That means f is a contraction on H of x. Now, what do you mean by the contraction? If you are taking two element a and b in H of x and find the image of a and b under the mapping f and find the distance between a and b in H of x, this number, if this number is less than or equal to some c time h d of a comma b, that we can already establish. This can be written as like this one as per this definition. Then each thing is contraction, therefore this contraction mapping, the union is contraction with contraction ratio maximum of this all the contraction, therefore this can be written as like this one. So, one can arrive that f is a contraction on the complete metric space. Now, the Banach theorem will play the role. F is a contraction on the complete metric space, then Banach theorem says that f has a unique fixed point. We can say that fixed point as a star. That means, what do you mean the fixed point? F of a star equal to a star. That what is f of a? F of a is the union of f k of a stars. Moreover, the Banach theorem says that if you taking this sequence convergence to the a star where arbitrary given b. So, with respect to the b, this convergence will vary. That will give the proper example. So, with respect to the this b, the convergence will vary. Now, you can observe from this equation a star we are taking and a star is written as union of 1 to n f I of a star. Each f I is a contraction. Then obviously f I of a star is contained in a star. F I of a star is contained in a star because each f I is the contraction, whereas a star is written as union of all these ai's. That means a I is written as finite union of its subsets. All the f I of a star are the subsets are the a star. That means the image of a star under the mapping f I is subset of a star. These images are subset of a star, whereas here a star is written as the subset. That means you are taking the set and this set is written as the finite copy of itself. As we already defined, the fractal can be written as the finite copy of itself, or a part of the object is reflected the whole, then we can say it is a fractal. Therefore, this fractal, this fixed point, a non-empty compact subset set A star obtained from the theorem 2 is called the invariant set, because it is a fixed point equally called as the invariant set, or self-referential set because it is satisfying the self-referential equation, or the attractor or the deterministic fractal of the IFS, this one. So, now we have the clear definition for what is the deterministic fractal. So, the deterministic fractal A star is a non-empty compact subset of a hyperspace of X, which is generated by the fixed point of HB mapping constructed by the some special type of iterated function system. The special type of iterated function system is that we are imposing the contraction condition. So, we can say a deterministic fractal is a non-empty compact invariant set of the Hutchinson mapping generated by the finite set of contraction mapping. We can call it as a deterministic fractal. Now, let us discuss or give the example of deterministic fractal. Now, I can take x as 0, 1. So, 0, 1 is the metric with respect to the usual distance or Euclidean distance. This pair forms the metric space. Now, this is a subset of R. Now, I am defining the two map f1 of x as 1 by 3x. That means, I have the function like this one 0, 1, 0, 1. I have the two function f1 as x by 3 and f2 of x as x by 3 plus 2 by 3, that means x plus 2 over 3. If you applying this mapping on this set, what will happen? f1 of this one 0, 1, then it will contract f1 contract 0, 1 to the 1, 3 here. This whole thing will be contract to here, that means 1 become 1 by 3 and 0 become 0. When you are applying the f2 on this set, then it will goes to 2, 3 to 1, that means 0 goes to 2 by 3, the 0 goes to 2 by 3 and 1 goes to 1, 1 goes to 1, here it will come to here. Now, you can take the union of these two sets. If you are taking the union of these two sets, you will get 0, 1 by 3 union 2 by 3, 1, this two interval we will get. And if you are finding the contraction factor for these two mapping, the contraction factor of f1 is 1 by 3 and the contraction factor of f2 is also, this will cancel while applying the mapping, it is also 1 by 3. If you are defining the Hutchinson mapping as the union of f1 and f2, then this also contraction, it has the contraction factor of maximum of this one as 1 by 3 because both has the same contraction factor. Therefore, the contraction factor of these two is 1 by 3, that means that this map f is 1 by 3. Now, we will see what is the resultant attractors. Now, 0, 1 is the complete metric space with respect to the usual metric, no doubt. f1, f2 is the contraction mapping on this matrix, no doubt, and we defined the Hutchinson mapping on this one, then Hutchinson mapping also contraction, it must have the fixed point. Let us see what is the fixed point. So, with respect to these two mapping, how the iteration will act, let us take the b naught equal to 0, 1. With respect to the any random point, the attractor, the convergence will vary. So, finally, the sequence is convergent to the attractor, but with respect to the initial set or initial point, the convergence will vary. So, we are taking b naught as 0, 1 and define the sequence. What is this sequence? Bn is defined as f composition n of b naught, the same technique which we used to prove the Banach's fixed point theorem. Then what is B1? B1 is f1 of b naught. So, f1 of b naught means f1 of b union f2 of b naught. So, our b naught is 0, 1. F1 will map the 0 comma 1 to the 0 comma 1 by 3. So, here it is not B, it is a B naught, and union F2 map this B naught to the F2 map B naught to the 2 by 3 comma 1. So, F1 is the union of these two number. Now, we need to find what is B2. So, B2 is F2 of B naught, which is equal to F of B naught, which is equal to F of B1. So, F of B1 is, we need to apply this mapping F on both the set 0 comma 1 by 3 union 2 by 3 comma 1, and both the set we need to apply on this set. Then F, if you want to apply this one, you can see if you are applying this one, that means the two mapping F1 will act on 0 comma 1 by 3 and F2 will act on 0 comma 1 by 3. So, in that case, if F1 if you are acting this one can get 0 comma 1 by 3 means 1 by 9. Yes, then union if you are applying this mapping, one can get 2 by 9 comma 1 by 3, 2 by 9 comma 1 by 3. Similarly, if you apply this F1 F2 on this set, then one can get 2 by 3 comma, that means 2 by 3 is 6 by 9 and 7 by 9 union 8 by 9 and 1, 8 by 9 and 1. Now, you can find what is the B3. So, in all the cases, one can observe that here we are started with the interval 0 comma 1. If you are applying F1 F2 on this set, we are getting this set 0 comma 1 by 3 and 2 by 3 comma 1. Now, again F1 and F2 acting on this set as well as F1 F2 acting on this set simultaneously, then one can get 0 comma 1 by 9 and 2 by 9 comma 1 by 3, and applying here one can get 2 by 3 comma 7 by 9 and 8 by 9 comma 1. Now, we need to apply F1 F2 on all the 4 interval. So, all the interval the mid one is missing, then final that it is a decreasing sequence, we have to take the intersection. In general, Bn is obtained by removing the middle third of the each interval of Bn minus 1. That means, in the nth step we are obtaining the set by removing the middle third of each sub interval in Bn minus 1. Thus, the limit of the sequence Bn converges to the classical Cantor set. That means, this set is convergent to the intersection of all the things. You can take the intersection of all one, you can get the fixed point. That fixed point we can call it as the Cantor set. Now, we have some logical construction of the Cantor set. We constructed the Cantor set as a fixed point of the Hutchinson mapping with respect to the two specific contraction F1 and F2 given here. So, in this way we can construct the fractals. Now, the question is, we have constructed the Cantor set by removing the middle third, whereas this attractor, as per the theorem, the attractors is based on the iterated function system. If you are changing the space and the contraction, your attraction will vary, as well as if you are simply changing the contraction factor also, your attractor will vary, you will get the different attractor. So, your attractor, the convergence is depends on the initial points, but finally it will convert the fixed point, whereas this attractor is depends on the iterated function system. If you vary the space, if you vary the contraction, one can get the different type of attractor. No doubt it is not same for all the iterated function system. Now we will check if you, instead of changing the space and the mapping, now will let us change simply the contraction factor, then what will happen on the attractor. For that we will take the Cantor type set. So usually in the construction of Cantor set, we divide the unit interval into 3 equal parts and removing the mid one. Now I divide this one by 4 equal parts and removing the mid 2 parts. So that means after the first iteration I can get the left side and right side, 1 by 4, 2 by 4 and 3 by 4 and 1. So I removed this middle one. Again I divide this one as 4 equal part and removing the middle, dividing 4 equal part and removing the middle. You can see there is a variance here. I can get this type of Cantor set. So the limiting is it is not a Cantor set, it is a Cantor type sets, because the Cantor set usually we are dividing 3 equal part and removing the middle. Now we are dividing 4 equal part and removing the middle. At each step remove the open middle quarter of each remaining interval. This is the construction rule. So if you are constructing, the limiting case is like this one. If you are taking all the intersection, after some certain iteration we will get this type of things. So obviously it has a similar property like the Cantor set. It is the uncountable set, its length is 0, like that. It has a closed set and perfect set, it has the same things. Now let us try to find the, or try to construct this 1 by 4 Cantor type set by the iterated function system. See, in the previous mapping we are taking f1 of x as x by 3. Here I am changing, instead of 1 by 3 I am taking 1 by 4, just small changes. Instead of 1 by 3 I am taking 1 by 4, there is a small changes. And similarly here x by 4 plus 3 by 4 I am taking, instead of 3 I am taking the 4. Then each fk, this f1 f2 is contraction with the contraction ratio 1 by 4. Apply the Hutchinson mapping or define the Hutchinson mapping by defining the union of this one. So both are contraction, therefore their union is contraction. In the same, the Hutchinson mapping is the contraction on H of R. That means we are taking here we need to take it is as a complete matrix. Yes, we can take the whole R, or instead of here we can take 0, 1, because this is also complete metric space, not an issue. But if you want to specifically find the Cantor type set in the closed interval 0, 1, instead of R we can take 0, 1. Then by the theorem 2, this Hutchinson mapping has a unique non-empty compact set, that means the invariant set for this mapping F, that we can call it as A star. This fixed point A star is called Cantor type fractal or Cantor type deterministic fractal obtained from this two iterated function system. Here iterated function system is, we can take 0, 1 specifically, not R. R means we will get different things, 0, 1 and F1 and F2. So this is by removing the middle open half of each subinterval repeatingly, we will get this one. This is, we can call it as the thing. So now if you are applying the F1 0, 1, you will get 0, 1 by 4. If you are applying the this one, will get then F2 of 0, 1, one can get like the similar type of Cantor sets we can get. For previous one also we can construct it like this one, we can get this 4 interval, and then this sequence convergence to the 1 by 4 Cantor type sets, middle 1 by 4 Cantor type sets. Now, you can just recall in the first module, in the first lectures, I have constructed some other the fractals which has the self similar nature. We called it as a classical fractals. It is a Sierpinski triangle, Van Koch curve, and also the Cantor set. The Cantor set now we constructed by using the iterated function system. Now, whether is it possible to construct the same fractal, that means Sierpinski triangle and the Van Koch curve by the iterated function system? Yes, for that we need to properly define the iterated function system, then it will generate the Sierpinski gasket. So, if you are taking the closed interval 0, 1 and their Cartesian product, and A and B and C are 3 vertices, if you are taking 3 contraction F1, F2, F3 like this one, this is 1 by 2, 1 by 2, and here also the contraction factor is 1 by 2, here also the contraction factor is 1 by 2. Then these 3 contraction mapping on this set equilateral triangle ABC on 0, 1 cross 0, 1, this is the complete metric space. We can define the Hutchinson mapping as by taking the union of F1, F2, F3, then this will generate the fixed point. That fixed point will give the our resultant Sierpinski triangle or gasket. And similarly, if you are taking the X as this space and 4 contraction F1, F2, F3, F4 defined by like this one, all these 4 mappings are contraction with the contraction factor 1 by 3. Then if you define again the mapping F of any set from this X, A as the union of I equal to 1 to 4 Fi, then this has a fixed point in this space X, that means H of X, that the fixed point that means that fixed point is nothing but the Koch curve. So, like similar to the Cantor set process, one can construct the Koch curve by using this iterated function theorem. So, in this lecture we have defined what is the deterministic fractal. So, deterministical fractal, if we have one iterated function system, on the iterated function system we can define the HB mapping, then the HB mapping is a contraction and it has a fixed point in H of X. That fixed point we can call it as a deterministic fractal. A deterministic fractal is a fixed point of the Hutchinson mapping generated by the specific type of iterated function systems. Thank you. These are all some references one can refer. Thanks.